Hi guys, this is your second pre-recorded video for you to watch. Make sure today on Canvas that you look at the homework, you submit your homework, and you fill out the Google form so I know any questions we need to go over tomorrow. And so let me switch over to my document camera. So these notes are available on Canvas if you want to print them off, but I do want to remind you that you learn when you write things down, so even if you didn't print them off, make sure you're writing them down. So as we're looking at today's notes, we are going to start looking at geometric sequences. And the definition of a geometric sequence is it's a sequence where the ratio between consecutive terms is the same. So consecutive means back-to-back terms, and we'll look more at that in a second. And that ratio has a special name to it, and I have a hole punch right through the name of this. That should say common ratio. And the common ratio is the ratio between those consecutive terms. And so what I want you to do for just a minute is I want you to pause the video, see if you can fill in the two tables below, graph, and tell me what R is. So go ahead and pause the video. Alright, so here we go. You should have had a chance to pause the video, and as we look at these two functions, we can see in the first pattern, the first function, our R value is 2. If you take 4 and divide it by 2, you get 2. Take 32 and divide it by 2, you get 2. And we were able to fill in our table. In our second pattern, we see that R is 1/3. It's what we're multiplying by every time. If we take 9 and divide it by 3, it's 1/3. 27 over 81, it's 1/3. So that's the value of R. And so notice I have dots on the paper here. I did not connect those, and that's because the domain, or the X values, of a sequence, and we mentioned that when it came to arithmetic. So remember, our domain is we have a term 1, we have a term 2, we have a term 3, we have a term 27. We do not have term 1.3. Okay? We don't have term -6. Now, they can have values, our Y values or our outputs, also called range, can have those values, but not our domain. And so that's why I've written here that these are exponential functions, but the domain are natural numbers. Natural numbers are also called counting numbers. So your domain is 1, 2, 3, 4, 5, 6, 7, and so on. So how does R relate to your graph? Well, you can see that that's your multiplier every single time. That's your multiplier every single time. Write the recursive formula. Now, as a reminder, the recursive formula has two parts to it. So first, I need to even know what term I'm going to multiply. And I can use a lot of different things. I'm going to, for this first example, say that A1 is 2. And actually, let's change it up on the second one. Let's use the fact that A3 is 81. That still gives us a number to multiply by. And then recursive formula is all about if you know the previous term, A sub n minus 1, what are you doing to that previous term to get A sub n? Well, every single time in this problem, I'm multiplying by 2. In the other problem, what am I doing to the previous term to get the term I'm looking for? I'm multiplying by 1/3. Okay, so next we're going to take a look at the explicit formula sum. And I noticed when you guys were looking at your open or your homework from Monday night, a lot of you just looked up a formula. Well, we want to know exactly where that formula comes from. So let's go look at the pattern we see in problem number 1 for just a second. So we're looking at a pattern. This is really what I want you to understand. Here's term 1. How did we get 4? We took term 1 and we multiplied it by 2. How do we get 8? Well, you're taking 4 and multiplying it by 2. Well, now then the question becomes, where did we get 4 from? We took 4 and it was 2 times 2. Okay, let's go to 16. How did we get 16? We took 8 and multiplied it by 2. Well, how did you get 8? It was 2 times 2 times 2 times 2. Okay, so I want you to hold that thought for just a second. Let's get back up here to problem number 1. How did we get 243? Well, we took 729 and multiplied it by 1/3. How do we get 81? We took 243 and multiplied it by 1/3. Well, what was 243? 729 times 1/3. By the way, how can I write 1/3 times 1/3? Okay, how do I get 27? So 27, I got it by taking 81 and multiplying it by 1/3. Well, where did 81 come from? It came from taking 729 and doing 1/3 squared. And then to get 27, I still have 1/3. So in other words, I could write this as 729 to the 1/3 cubed. You see a pattern yet? Let's go. How would we get 9? To get 9, I would take 27 and multiply it by 1/3. But how did I get 27? 27 is 729 times 1/3 cubed. So in other words, 729 times 1/3 to the 4th. So look at your pattern. To get the second term, I multiply by 1/3 one time. To get the third term, I multiply by 1/3 twice. To get the fourth term, I multiply by 1/3 3 times. To get the fifth term, I multiply by 1/3 4 times. How would I get the nth term? Or a sub n, I should say. Well, I'm going to take 729 and multiply by 1/3 n minus 1 times. So that's my explicit formula for this example. Okay, so think about it. We actually used a point. We used the fact that the first term was 729. Okay, let's go to second example. Will that follow suit? Okay. So we started with the number 2, and to get 4, we multiplied by our common ratio 1 time. So for 8, we start with 2, and we multiply by our common ratio twice. So in other words, 2 squared is what we multiply by. To get 16, we're starting with our first term. We'll come down here. And we multiply by 2, 2, and 2. So we multiplied by 2 3 times. So is our pattern still working? Are we still taking the first term and multiplying by our common ratio n minus 1 times? I think so. And again, we're using the fact that term 1 has a value of 2 there. So notice this next question says, write an equivalent explicit formula. Okay. So some of you may have done this problem pretty easily. Go back and look at your pattern. Could we not have said 4 is 2 squared and 8 is 2 cubed and 16 is 2 to the 4th and 32 is 2 to the 5th? In other words, could we not have said a sub n equals 2 to the nth? Which, by the way, oh no, we won't talk about that yet. So that's one example. Okay, let's go over here. What if instead of telling you the first term was 729, I told you to use that the second term was 243? How could you use that? Well, your common ratio, that multiplier has not changed. That multiplier is still 1/3. But now you're going to take 243 and multiply it by 1 n minus 2 times. Try it out. We know that our second term should be 243. If you plug 2 in, it's 1/3 to the 0. Well, that's 1 times 243, we get 243. Plug a 3 in. We know our third term should have a value of 81. 3 minus 1 is 1. 243 times 1/3 is 81. Actually, we could write this a whole bunch of different ways. We could use the fact that the fifth term is 9 and say that 9 times 1/3 to the n minus 5 will give us the same thing. So there's actually a whole lot of ways we can write these explicit formulas, and we'll look more at that in our next video. So I wanted to end here because we're looking at this discussion. So what I want you to focus on is not so much that there's a formula. I want you to know how it works. Okay, we're going to try really hard not to memorize a lot of things, but to understand them as we're working through our stuff.